Hello, everyone. My name is Nathan Sauerhagen. My capstone is on the economic impact of snowfall and snow depth on tax revenue in Colorado ski towns. This is for my master's in data analytics from Colorado State University Global. Revenue from winter tourism is vital for Colorado ski towns, but snowfall and snow depth variability create financial uncertainty for local businesses and governments. The ski industry can impact local Colorado communities by over $4.8 billion annually. The general perception is that more snow generates higher revenue and less snow means for more financial uncertainty. The ski season ranges from November through April, and snow fluctuates throughout the seasons and yearly. The relationship between snow variability and financial success in Colorado has been historically inconsistent and tumultuous. The focus of this capstone is on Breckenridge, Vail, Winter Park, and Dillon. The time frame ranges from 2021 through April of 2024 and focuses on the general sales tax, restaurant and bar sales tax, and lodging sales tax revenues. The research questions proposed is what is the statistical relationships between snowfall, snow depth, and tax revenue in Colorado ski towns? Can snowfall or snow depth be used as a reliable predictor for future tax revenue? And how can businesses and governments use these insights to improve financial planning? Previous literature review on this includes focus on the economic contribution of skiers and winter tourism has been primarily European focus. Research gaps include a lack of focus on tax revenue and predates 2020/COVID-19. The contribution of this study is to link prior European research to Colorado ski towns and to continue the ongoing research on the economic impact of seasonal variability on ski towns. Data sources utilized during this analysis are the National Oceanic Atmospheric Administration, NOAA, and local government reports and municipal financial records. Statistical techniques include descriptive statistics, correlation analysis, linear regression, and an Aramax time series modeling. Tools used are Python, SAS, and Excel. Some limitations of this analysis include economic variables not included, like inflation, price changes, and other external factors. External events like ski competition or mountain town events, which are not impacted by snowfall or snow depth, as well as the limited time frame, which results in a limited data quantity. Ethical concerns include data privacy, in which only publicly data was utilized and all sources have been verified, data taken from the original source, and is considered objective, consistent, and unbiased. Research acknowledges that there are limitations and does not embellish on the findings. Reviewing the descriptive statistics, all the locations and categories have the same number of snow depth, snowfall, and revenue variables in their analysis. Different amounts between the two based on how the categories are grouped, but each analysis of the locations and tax categories are consistent within themselves. There are also limited outliers impacting the analysis, which is indicated by the relatively low skewness and kuratosis. A skewness of 0 indicates a symmetric distribution, and a kuratosis of 0 indicates a normal distribution. The Winter Park revenues has the highest location kuratosis and skewness at 1.42 and 1.36, respectively, indicating moderate tail heaviness and some concentration of higher values. These are not excessive and do not significantly impact the analysis. Looking at the tax category summary statistics, lodging and accommodations has the highest skewness and kuratosis of the category variable, but similar to above, this does not significantly impact the analysis. Looking at the correlation analysis, a correlational analysis is a statistical method to assess the strength and direction of the relationship between two or more variables. The correlation coefficient, R, is the result of the correlation analysis, in which 0 indicates there is no relationship between the variables, where 1 indicates a perfectly positive relationship, indicating that as one increases, the other does as well. Looking at our results, we can see that snow depth has a moderate correlation with the lodging tax and restaurant bar tax revenues, while the remaining have a weak correlation. Looking at the graph on the right, we can see that overall snow depth has a higher correlation to revenue than snowfall in all categories. Turning to the linear regression. Linear regression is a statistical technique used to model and predict the relationship between the dependent variable, which is revenue, and one or more of the independent variables, snowfall and snow depth, by fitting a straight line. The goal is to find the best fitting straight line, which is one of the most common techniques in predictive modeling and data analytics. The p-value indicates the statistical significance of the relationship between the dependent and independent variables. And throughout this capstone, the statistical significant threshold is 0.05. This means that any p-value underneath 0.05 is considered statistically significant, while anything over that is considered not statistically significant. Looking at these results, we can see that overall the snow depth is considered more statistically significant and has the highest statistical significance, with the restaurant and bar coming in at 0.001%. Looking at the graphs on the right, we can see that the shaded area shows that 95% confidence in the intervals of the predicted revenue values. The goal is to have a narrow, more precise predictions. These graphs also include the R-squared values, which shows the portion of the variance in the independent variables, snowfall and snow depth, that can be explained by the linear relationship with the dependent variables. The graphs on the right include restaurant bar tax revenues from both snowfall and snow depth because they have the highest statistical significance in both. Looking at these results, though, we can see that the R value for snowfall shows that 6.83% of the variability in the revenue can be explained by the snowfall. Similarly, for snow depth, this can show that 19.38% of the variability in the revenue can be explained by the snow depth in this linear regression. While these variables are statistically significant, these models cannot accurately predict a significant amount of the variability in the revenue. Turning to the modeling and forecasting, this utilizes an Aramax modeling, which is a time series forecasting and is one of the most widely used and effective methodologies for predicting future values based on past observations. The models on the left are the distribution of residuals, which shows the difference between the observed values, which are the actual revenue values, and the predicted values or forecasted revenue values. The blue curve is the normal distribution curve, showing an ideal model that the residuals should follow. The red curve is the kernel density estimate and is a smooth approximation of the residual distribution, which detects the skewness and other features that might indicate issues with the model's accuracy. These results show that on the snowfall, the residuals are heavily skewed, with a significant peak near zero, indicating that the model may not be perfectly accurate and the predictions have some bias and errors. Similarly, snow depth also has some biases and errors, but is a better fit than snowfall. Looking at our conclusions, the snow depth has a stronger correlation and is more statistically significant. Snow depth based linear regression models are also the most reliable for predicting the future tax revenues, but only accurately account for 19% of the variability in the tax revenue. Recommendations going forward is local governments can utilize this information to integrate snow depth into tax revenue forecasting. They can use snow depth data for infrastructure planning and develop contingency plans for low snow years. Businesses can use snow depth projections to optimize pricing strategies, staffing, resources management, and adjust operating hours based on projected snow depth levels. They can also generate artificial snow to stabilize economic activity when necessary at ski resorts. For future research, incorporating additional economic variables and future studies could improve the viability of the research. Also, segmenting ski seasons to better account for seasonal variability, as well as expanding the data sets and including additional locations, would be recommended for future analysis.